In this chapter, we focus about polar covalent bonds, acids, and bases. The first, we need to know about the electronegativity. When two atoms of different elements are linked by a covalent bond, the shared electrons are not attracted equally by the two nuclei of bonding atoms. The polarity of bond gives partial ionic character. These are polar covalent bonds. Bonding electrons attracted more strongly by one atom than by the other. Electron distribution between atoms is not symmetrical. What is the electronegativity? The electronegativity intrinsic ability of an atom to attract the shared electrons in a covalent bond. Differences in electronegativity produce bond polarity. Electronegativities are based on an arbitrary scale. Fluorine is most electronegative, En equals 4.0, cesium is least, En equals 0.7. Metals on left side of periodic table attract electrons weakly, lower electronegativities. Halogens and other reactive nonmetals on right side of periodic table attract electrons strongly, higher electronegativities. Electronegativity of C equals 2.5. Non-polar covalent bonds, atoms with similar electronegativities. Polar covalent bonds, difference in N of atoms is lower than 2. Ionic bonds, difference in electronegativities is higher than 2, approximately. Other factors, solvation, lattice energy, etc., are important in ionic character. Bonding electrons are pulled toward the more electronegative atom in the bond. Carbon acquires partial positive charge. Electronegative atom acquires partial negative charge. And now, we talk about the inductive effect. The inductive effect is the shifting of electrons in a bond, in response to the electronegativities of nearby atoms. When a covalent bond is formed, between atoms of different electronegativity, the sigma electrons of the bond get shifted towards the more electronegative atom of the bond, that results in polar covalent bond. Chlorine being the most electronegative, draws some electron density towards it in such a way, that the carbon 1 gains some positive charge delta plus, and the chlorine some negative charge delta minus. In turn C1, which has developed partial positive charge delta plus, draws some electron density towards it from the adjacent C-C bond. Consequently, C2 develops some positive charge 2 delta plus. Similarly, C3 develops some positive charge 3 delta plus, due to the presence of partial positive charge 2 delta plus on C2. The order of inductive effect is 3 delta plus lower than 2 delta plus lower than delta plus. Inductive effect weakens steadily with increasing distance from the substituent, electron withdrawing or electron donating group. Inductive effect becomes vanishingly small after 3 bonds. There are 2 types of inductive effects. Minus inductive effect. Plus inductive effect. Minus inductive effect. If the substituent attached to the end of the carbon chain is electron withdrawing, the effect is called minus inductive effect. The minus inductive effect of some of the atoms and groups in decreasing order is nitro, nitrile, carboxyl, fluorine, chlorine, bromine, iodine. Plus inductive effect. If the substituent attached to the end of the carbon chain is electron donating, the effect is called plus inductive effect. Plus inductive effect of some of the atoms or groups in the decreasing order is tert-butyl, isopropyl, ethyl, methyl. Now we focus on formal charges. Sometimes, it is necessary to have structures with formal charges on individual atoms. We compare the bonding of the atom in the molecule to the valence electron structure. If the atom has one more electron in the molecule, it is shown with a minus charge. If the atom has one less electron, it is shown with a plus charge. Formal charges equals number of valence electrons in free atom, minus number of valence electrons in bound atom. Equals number of valence electrons minus half of bonding electrons minus number of non-bonding electrons. In the nitromethane molecule, formal positive charge on nitrogen atom, formal negative charge on oxygen atom. The calculation of formal charges for the nitromethane. For the nitrogen atom, nitrogen valence electrons equals 5. Nitrogen bonding electrons equals 8. Nitrogen non-bonding electrons equals 0. Formal charge equals 1. For the oxygen atom, oxygen valence electrons equals 6. Oxygen bonding electrons equals 2. Oxygen non-bonding electrons equals 6. Formal charge equals -1. Look at the table, you can see the carbon, nitrogen, and oxygen atom with plus, 0 and minus formal charges. And now, I would like to talk about resonance. Some molecules have structures that cannot be shown with a single Lewis representation. In these cases, we draw Lewis structures that contribute to the final structure, but which differ in the position of the pi bonds or lone pairs. Such a structure is delocalized and is represented by resonance forms. The resonance forms are connected by a double-headed arrow. Resonance hybrids. A structure with resonance forms does not alternate between the forms. Instead, it is a hybrid of the two resonance forms, so the structure is called a resonance hybrid. For example, benzene has two resonance forms with alternating double and single bonds. In the resonance hybrid, the actual structure, all of the CC bonds are equivalent, midway between double and single bonds. These are two resonance forms of benzene. And two resonance forms of acetate ion. Rules for resonance forms. Individual resonance forms are imaginary, the real structure is a hybrid. Only by knowing the contributors can you visualize the actual structure. Resonance forms differ only in the placement of their pi or non-bonding electrons. Different resonance forms of a substance don't have to be equivalent. Resonance forms must be valid Lewis structures, the octet rule usually applies. The resonance hybrid is more stable than any individual resonance form would be. Curved arrows and resonance forms. We can imagine that electrons move in pairs, to convert from one resonance form to another. A curved arrow shows that a pair of electrons moves from the atom or bond at the tail of the arrow, to the atom or bond at the head of the arrow. The red curved arrow indicates that a lone pair of electrons moves from the top oxygen atom, to become part of an NO double bond. Simultaneously, two electrons from NO double bond move onto the bottom oxygen atom, to become a lone pair. The new resonance structure has a double bond here, and has a lone pair of electrons here. Any three-atom grouping with a multiple bond has two resonance forms. Sometimes resonance forms involve different atom types as well as locations. The resulting resonance hybrid has properties associated with both types of contributors. The types may contribute unequally. The enolate derived from acetone is a good illustration, with delocalization between carbon and oxygen. The anion derived from 2,4-pentanediene. Lone pair of electrons and a formal negative charge on the central carbon atom, next to a CO double bond on the left and on the right. Three resonance structures result. Draw three resonance forms of the pentatedienyl radical. From three-atom grouping, we draw the resonance. From the next three-atom grouping, we also draw the resonance. Acids and bases, the Brønsted-Lowry definition. Brønsted-Lowry theory defines acids and bases by their role in reactions that transfer protons between donors and acceptors. Proton is a synonym for H+, loss of an electron from H leaving the bare nucleus, a proton. Protons are always covalently bonded to another atom. Brønsted-Lowry is usually shortened to Brønsted. A Brønsted acid is a substance that donates a hydrogen ion, or proton, H+, a proton donor. A Brønsted base is a substance that accepts the H+, a proton acceptor. The reaction of hydrogen chloride with water. When hydrogen chloride gas dissolves in water, a Brønsted acid-base reaction occurs. Hydrogen chloride donates a proton to water molecule, yielding hydronium ion, H3O+, and chlorine-. The reverse is also a Brønsted acid-base reaction of the conjugate acid and conjugate base. You can see here, the reaction of acid and base to form the conjugate base and the conjugate acid. Quantitative measures of acid strength. The equilibrium constant, Keq, for the reaction of an acid with water, to form hydronium ion and the conjugate base, is a measure related to the strength of the acid. Stronger acids have larger Keq. Note that brackets indicate concentration, moles per liter, m. The concentration of water as a solvent does not change significantly when it is protonated in dilute solution. The acidity constant, Ka for Ha, equals Keq, times 55.6 m, leaving water out of the expression. Ka ranges from 10 to the power 15 for the strongest acids, to very small values, 10 to the power -60, for the weakest. Acid and base strength. The ability of a Brønsted acid to donate a proton to, is sometimes referred to as the strength of the acid. The strength of the acid can only be measured, with respect to the Brønsted base, that receives the proton. Water is used as a common base for the purpose of creating a scale of Brønsted acid strength. pKa, the acid strength scale. pKa equals minus logarithm Ka, in the same way that pH equals minus logarithm of the concentration of proton. The free energy in an equilibrium is related to minus log of Keq. A larger value of pKa indicates a stronger acid, and is proportional to the energy difference between products and reactants. The pKa of water is 15.74. The larger the value of the pKa, the weaker is the acid. The stronger the acid, the weaker will be its conjugate base. We can, therefore, relate the strength of a base to the pKa of its conjugate acid. The larger the pKa of the conjugate acid, the stronger is the base. Predicting acid-base reactions from pKa values. pKa values are related as logarithms to equilibrium constants. The difference in two pKa values is the log of the ratio of equilibrium constants, and can be used to calculate the extent of transfer. Predicting acid-base reactions from pKa values. The general principle to apply is this: acid-base reactions always favor the formation of the weaker acid and the weaker base. The reason for this is that, the outcome of an acid-base reaction is determined by the position of an equilibrium. Acid-base reactions are said, therefore, to be under equilibrium control, and reactions under equilibrium control always favor the formation of the most stable, lowest potential energy, species. The weaker acid and weaker base are more stable, lower in potential energy, than the stronger acid and stronger base. Because there is a large difference in the value of the pKa of the two acids, the position of equilibrium will greatly favor the formation of the products. In instances like these we commonly show the reaction with a one-way arrow even though the reaction is in equilibrium. Organic acids and organic bases. The reaction patterns of organic compounds often are acid-base combinations. The transfer of a proton from a strong Brønsted acid to a Brønsted base, for example, is a very fast process and will always occur along with other reactions. Organic acids. Those that lose a proton from OH, such as methanol and acetic acid. Those that lose a proton from CH, usually from a carbon atom next to a CO double bond. Anion is stabilized by having negative charge on a highly electronegative atom. Anion is stabilized by having negative charge on a highly electronegative atom and by resonance. Anion is stabilized by resonance and by having negative charge on a highly electronegative atom. Some organic acids. Methyl alcohol, pKa equals 15.54. Acetic acid, pKa equals 4.76. Acetone, pKa equals 19.3. And conjugate bases of acids. Organic bases have an atom with a lone pair of electrons that can bond to H+. Nitrogen-containing compounds derived from ammonia are the most common organic bases. Oxygen-containing compounds can react as bases when with a strong acid, or as acids with strong bases. Some organic bases. The methylamine is containing the nitrogen atom. The methyl alcohol is containing the oxygen atom. The acetone is also containing the oxygen atom. Acids and bases, the Lewis definition. Lewis acids are electron pair acceptors, Lewis bases are electron pair donors. The Lewis definition leads to a general description of many reaction patterns, but there is no quantitative scale of strengths as in the Brønsted definition of pKa. Lewis acids and the curved arrow formalism. The Lewis definition of acidity includes metal cations, such as magnesium 2+. They accept a pair of electrons when they form a bond to a base. Group 3A elements, such as boron trifluoride and aluminum chloride, are Lewis acids because they have unfilled valence orbitals and can accept electron pairs from Lewis bases. Transition metal compounds, such as titanium tetrachloride, iron 3 chloride, zinc chloride, and tin tetrachloride, are Lewis acids. Organic compounds that undergo addition reactions with Lewis bases, discussed later, are called electrophils and therefore Lewis acids. The combination of a Lewis acid and a Lewis base can show with a curved arrow from base to acid. Illustration of curved arrows in following Lewis acid-base reactions. Some Lewis acids. Water, hydrogen chloride, hydrogen bromide, nitric acid, sulfuric acid. A carboxylic acid, a phenol, an alcohol. Some cations, lithium 1+, magnesium 2+, bromine plus. Some metal compounds, aluminum chloride, boron trifluoride, titanium tetrachloride, iron 3 chloride, zinc chloride. Lewis bases. Lewis bases can accept protons as well as other Lewis acids, therefore the definition encompasses that for Brønsted bases. Most oxygen and nitrogen containing organic compounds are Lewis bases because they have lone pairs of electrons. Some compounds can act as either acids or bases, depending on the reaction. Some Lewis bases: an alcohol, an ether, an aldehyde, a ketone, an acid chloride, a carboxylic acid, an ester, an amide, an amine, a sulfide. You can see here some of acid-base reaction. Thank you for your attention.